Yeah, the lecture slides are posted in the Discord on, I think, the events page. Okay. Let's see. Yeah, okay, should we go ahead and get started?
Yeah, go ahead.
Okay. Hi, everyone. Welcome back. If you haven't been here before, my name is Jahan. I'm a postdoc at Yale, and I work on quantum error correction. Today is the third and final lecture on how we do quantum error correction for quantum computers. And so in the first week, what we talked about was essentially why we need quantum error correction. I think a few people need to mute themselves, just FYI. Last time we saw some examples of how, or 2 weeks ago, we saw some examples of how we might need quantum error correction and how errors can totally swamp a computation.
I don't know whether it's good. What? I think something shit.
And how, yeah, errors can totally swamp a computation. Last week, we talked about some simple examples of stabilizer codes. And what we did there was we saw an example of the repetition code and then an example of Shor's code and how those could correct single qubit errors. And so today we're going to go and try and correct kind of arbitrary errors, where errors can happen simultaneously on many qubits, and we'll still be able to correct them. And that's kind of the state of the art right now, and it's called the surface code. So let's start with a review of what we did last time, because like I said last time, the surface code is just the stabilizer code, and we're going to use the same stuff we did to think about Shor's code as we are going to do for the stabilizer code. So as a reminder, what are stabilizers? So stabilizers are just a list of operators, a list of observables that we write down that are always supposed to equal 1 if our code didn't do something wrong. So if there was no error, we're supposed to just be able to measure these operators over and over and just get back 1 every single time we measure them. And so what is quantum error correction? Quantum error correction is we repeatedly measure these stabilizers over and over and over again and just make sure they're 1. And we can do that without changing the quantum state, because the quantum state is going to be in a superposition of 2 states that both have these observables equal to 1. So we don't collapse our superposition just by measuring. So we also saw 3 rules that you had to follow if you wanted your stabilizers to properly define a code. So our first rule was how these stabilizers can detect errors, because a single stabilizer can't detect arbitrary errors. What we saw was a stabilizer with an X on a certain qubit can detect Z errors on the qubit that it has an X on. And similarly with Z's and X's. So if you have a Z in your stabilizer, that Z detects X errors. And rule 2 is that if we have a set of stabilizers, they have to be compatible. And what do we mean by compatible? We mean that 2 stabilizers are compatible if they disagree on, and I'm so sorry, this is a typo. They have to disagree on an even number of qubits. So 2 stabilizers could just agree on all qubits. That's fine. Or they could disagree on 2 qubits, or they could disagree on 4 qubits, or whatever. And then the third rule is that 2 errors on a stabilizer looks like no errors on a stabilizer. So if your stabilizer can detect single errors, but if there's 2 errors on the qubits that the stabilizer works on, it won't detect them. So as an example, we have the repetition code where there are just 2 stabilizers, Z1, Z2, and Z2, Z3. And so just as a reminder exercise, what are the states psi that are stabilizer states for this code? So what are the states psi that have Z1 times Z2 equals 1 and Z2 times Z3 equal 1? And anyone can either unmute themselves and answer, or you can answer in the chat. but somebody's got to answer. If you want to answer part of the question, you can. For example, you could tell me a state with Z1, Z2 equal to 1. Let's see what's going on in the chat. So yeah, so one state is 0, 0, 0, 0. That has the first two are both like Z on the first and Z on the second is both +1. So if you multiply them together, you get +1. And similarly, if you do the second and the third, and then for 1, 1, 1, the first one is -1, the second one is -1. If you multiply them together, you get 1, and similarly for the second and the third. So our general answer is, yeah, a superposition of 0, 0, 0 and 1, 1, 1. And then second exercise, what happens to these stabilizers if an X1 error happens? And you can either write this down directly, or you can think about the 3 rules that I've written to the side. But so we have the state, alpha 0, 0, 0 plus beta 1, 1, 1. And then we accidentally apply an X1 operator. So an X operator happens to the first qubit. And then we try and measure the stabilizers again. And so what are the stabilizers going to say? Just putting a reminder up here, people who want to think about it this way. Okay. Yeah, so that's right. So if we measure Z2, Z3, we're going to get back to things. Somebody have a question? No? Okay. So yeah. So if we measure Z1, Z2, we're going to get back -1. But if we measure Z2, Z3, we're going to still have +1. And like, there's lots of ways to see this, but the way I want us to think about it for the rest of this lecture is by rule 1. So by rule 1, X errors are detected by the stabilizer Z1, Z2. So X errors on the first qubit are only detected by this stabilizer. They're not detected by the Z2, Z3 stabilizer because the Z2, Z3 stabilizer doesn't touch qubit 1. So this stabilizer is detecting X errors on qubits 1 and qubit 2. So it goes off, it measures -1. And then finally, what happens to the stabilizers if an error X1, X2 happens? So we get an X error on the first qubit and the second qubit simultaneously. And then this will be the last review exercise. Sorry, I think you're cutting out for me. Maybe try saying it again or putting it in the chat. Sorry. So Z2, Z3 will give -1. So that's true. And what will Z1, Z2 give? Okay, great. Yeah. So so by rule 1, we know that both Z1 and Z2 and Z2 and Z3 can detect X errors. But Z1, Z2 got hit with 2 errors, which means that it seems like no errors. The first error flipped its sign, but then the second error flipped its sign again. And if you flip your sign twice, you're back to where you started. So the first stabilizer doesn't see the error, and the second stabilizer does. And so this might be an error that we misidentify, because we might think it's an X3 error, even though it was an X1, X2 error. Okay, great. So now we're time to talk about the surface code. And so what is the surface code? The surface code is just a stabilizer code, but it has a lot of stabilizers. So we're going to have to think about it carefully. So the way you get the surface code is you're looking at a 2D grid of qubits. So every dot here is its own qubit. So I've done 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25 qubits. We're going to take 25 qubits and we're going to store a single qubit inside them. That's the way I've drawn it. And so to tell you what the code is, I should just tell you what stabilizers we're going to measure. And so here they are. So on every square, there's a stabilizer that's either 4 X's or 4 Z's. So just to make sure we understand what these stabilizers are, because there's a lot of them. There we go. Sorry, the animations got a little messed up. So let's look at, for example, the stabilizer on this A that I've labeled. So by this, I mean that if I've labeled these qubits as 1, 2, 3, 4, 5, 6, 7, A has an X on qubit 1, an X on qubit 2, an X on qubit 3, and nothing on any of the other qubits. B has a Z on qubit 2, a Z on qubit 3, a Z on qubit 4, and a Z on qubit 6. And then C has a Z on, or sorry, has an X on qubit 3, 5, 6, and 7, and so on and so forth. I'm not labeling all the qubits just because there's a lot of them. But the idea is this stabilizer has a Z on the 4 corners. This stabilizer has an X on its 3 corners, and on and on. And notice that I've carefully constructed this so that I have these on one edge, I've defined these triangles so that they have X's in them, and on the other edge, we've defined the triangles to have Z's in them. And let's just do a quick sanity check. Are these stabilizers compatible? So as a reminder, rule 2 says, with the typo, 2 stabilizers are compatible if they disagree on an even number of qubits. So let's go ahead and check that this is true. Do all of these stabilizers disagree on an even number of qubits? Well, for example, if we look at A and B, they disagree on qubits 2 and 3 because they disagree on both qubits on their boundary. B and C, they disagree on qubits 3 and 6, both qubits on their boundary, so that's an odd number. And then if we look at A and C, well, they only touch at qubit 3, but they agree on qubit 3. So they disagree on 0 qubits, which is an even number. So these are all going to be compatible. And obviously, like this plaquette and this one over here agree because they don't disagree on any qubits because they're so far away. So if you're right next to someone, you disagree on 2 qubits. If you're across from someone, you disagree on no qubits. And if you're far away, you obviously disagree on no qubits. So all of these are compatible. Okay. So let me actually pause here and just ask, is there any questions about what I mean when I say these are the surface code stabilizers?
Yeah, I have a question.
Yes.
Yeah, why is it called the surface code?
This is kind of an accident of history. So the surface code was originally called the toric code because people thought you had to put it on a torus, which is like the surface of a donut. So you just kind of imagine, you can imagine to yourself that you roll this up so that like this side and this side touch. And instead of having these triangles at the edges, we just had, perfect squares going around the edges, and you roll it up so that this side and this side also touch. That's how you make a torus. It was realized pretty soon after that you could introduce these triangles at the edges, and it still works just fine. And so they called it the surface code because instead of being on the surface of a donut, they had done it on a two-dimensional just sheet of paper. So they called it the toric code if it was, rolled up, and then the surface code if they had flattened it out. And this was considered notable at the time that we could just do it on a surface and we didn't need to do it on a donut. But so this is why it's called the surface code. But more generally, there are codes that you need to have qubits laid out in 3D for. And the surface code, we're emphasizing surface because you only need to lay these qubits out in a two-dimensional layout. And that's kind of important because there are a lot of qubit platforms that you can't really wire them up in 3D, but you can definitely create like a two-dimensional sheet of them. Okay. Let's continue. So here's the surface code. Here's the two rules on how we decide what stabilizers detect errors. And the same rules apply as before, same as the repetition code, it's just that there's more stabilizers. And so now we're going to just try and think to ourselves, how does the surface code detect errors? Okay. So as an exercise, I want us to first think about some errors this surface code can't detect. And this is an interesting exercise for a few reasons. But I want you to think of putting down some X operators that the surface code can't detect. So you want to put down some X operators so that every stabilizer after this X error returns a value of +1. So just as a reminder, if we think about rule 1, if we put down X errors, the stabilizers with X's on them don't change. The only stabilizers that change are the stabilizers with Z's on them. So you just have to think about the Z stabilizers. And by rule 3, if you have 2 errors on a stabilizer, it looks like no errors on a stabilizer. So I want you to think about how that might happen and then maybe describe in words in the chat or unmute yourself what kind of errors you put down to make there be no Z stabilizers that detected any errors.
How about an X error followed by another X error?
Where am I putting these X errors? You mean like an X error here and then another X error there?
Yeah.
Yeah, so that's equivalent to no error because X is its own inverse. So this is correct, but I want something trickier to write down. I want there to be only single X errors on qubits. There will be a reason for this. So I want X errors on multiple qubits that look like no errors at all. So for example, if I put an X error here, that would flip these two plaquettes. I don't want them to be flipped. So this plaquette needs to have a second X error on it. Okay, so now this plaquette is fine. It's not detecting any errors, but now this plaquette is detecting an error. Similarly down here, this plaquette is fine. if I put an X error over here, but then this plaquette would detect an error. Harsh, what do you mean by X error on the diagonal? Let's think about that. Do you mean an X error here and an X error here?
I mean, extra diagonal of the surface.
Sorry, one more time. Your microphone isn't picking up.
So like, okay.
I think I can hear you now. Yeah, so okay, I think the correct answer is in the chat. So yeah, a few people said X errors on every corner of the square. And so that's definitely one of the answers. So let's let me clear off my screen. So as an answer, essentially you can draw any loop that touches Z's an even number of times. So if you draw a loop, for example, this loop of X errors, or that loop of X errors, or what people were saying in the chat, which is like just a single loop around a square, or sorry, not that. But a single loop around a square, like, let me go back, like that. Then you can't detect that error. And the reason is because each of these Z plaquettes has 2 X errors on it. And so the question is, should we worry about this? This seems like right away something bad about the surface code. There could be just 4 errors that it can't correct. And okay, 4 errors is not terrible. Like we saw that the repetition code, it couldn't correct even 3 errors. But it's still not great. We would like to do better than just correcting 4 errors. So the question is this a problem? And for the answer, let's look at this stabilizer. So let's think about what happens if those 4 X errors happen. So I'm going to call that XA, XB, XC, and XD to our encoded state that I'm going to call psi bar. What does acting on psi bar with these 4 errors give me?
It would remain psi bar because each one of these is an inverse of each other.
No, so these aren't inverses of each other because this is X on the first qubit and this is X on the second qubit. So for example, if I had 0, 0, 0, 0 and applied all of these X operators, I would get back 1, 1, 1, 1. So they're not inverses of each other. They really are doing something to the state because this X operator flips this qubit, that X operator flips that qubit. But it is true that these shouldn't do anything to our state. And there's a subtler reason for it. Can anyone tell me what that is? Why should this operator do nothing to our encoded state? What kind of operator? So this is related to degeneracy. But I want a more specific explanation here. I want you to tell me what kind of operator is this product of x's when I'm looking at this code. And maybe here's a hint. What are the operators that don't do anything to my state? What are those called? Right, those are stabilizers. The point is that the product of x's on these 4 qubits, x, 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 is a stabilizer. It's this stabilizer, which means that if I act on my encoded state with those 4 qubits, I'm supposed to just get 1. I'm just supposed to get my encoded state back. So these errors can happen, but if they do, they don't do anything to the state. So we can't detect them, but they also don't do anything to us. So we're very happy here. Similarly, if we think about this string of x's that has 6 x's, it's the product of this stabilizer times this stabilizer. So this loop also, if you take all of the x's in it and act on our encoded state psi bar, we just get back psi bar. And similarly, this loop over here is the product of that stabilizer and that stabilizer. So again, it doesn't do anything. These are all errors we can't detect, but we also don't care about it. Okay. So those are the errors we can't detect. What about the errors we can detect? Let's focus on those for a minute. Okay. So here's just a reminder. We're in where we have rule 1, what stabilizers detect what errors. And here's an exercise where I've given some labels to these plaquettes. So if an error X happens here, what do we get when we measure all the stabilizers? What stabilizers give -1, just according to rule 1?
Z6 should be -1.
Sorry, I don't know what Z6 is because that's not a stabilizer. The stabilizers are B, C, K, L, etc. And remember, we're not measuring qubit 6. We're measuring stabilizers. Okay, so I'm seeing a few answers in the chat. So by rule 1, if there's an X error on this qubit, it's going to flip the stabilizers that have Z's on that qubit. So B and K both have stabilizers on that qubit. On the other hand, C has an X on that qubit, so it doesn't detect that error. So just B and K get flipped. We flip the values of stabilizers with Z6 in them. So we get SB equals -1, SK equals -1, and all of the state +1. And so the punchline is that if there's an X error, it's like easy to visualize what's happening. It's easy to like kind of see this geometrically. We get minus signs on neighboring Z stabilizers. And then here I put up rule 1 and rule 3, and I'm going to ask you, okay, if we have 2 X errors where I've drawn them, what do we get when we measure all the stabilizers? What stabilizers give us back -1?
BKM.
So think about K for a minute. What's going on with K though?
Oh yeah, minus times minus, so it would remain in plus, I guess.
Exactly. So by rule 1, we should be looking at places with Z6s and Z7s in them. But by rule 3, if we have both Z6 and Z7, we get flipped twice. So SB and SM detect this error, but SK doesn't. So it looks like this. And some people like to visualize this kind of as a string, where the string goes through all your X's, and then you only detect the ends of the string. You don't detect the middle of your string. And so, for example, if there was like an X, X, X here, we would have this string. We don't detect the middle of the string, but we do get a minus over here and a minus over here. And we detect the ends of the string. And so what the surface code kind of works like is it gives us the ends of the string, and then we have to guess where the string was. That's the game. Okay. So now let's just think about Z errors for a minute. And I'm not going to make you do this because I think it's pretty straightforward. But so like, let's say a Z error happens here. Well, according to rule 1, we should be looking at stabilizers with X's on that qubit, which are just C and H. So it doesn't affect qubits up and down, but it does affect the neighboring qubits. So the point is a Z error on that qubit is going to flip the sign of the nearby X stabilizers. So again, X errors flip Z stabilizers, Z errors flip X stabilizers, which is just what you'd expect by rule 1 over here. Okay, so here I've written it out as a general rule for the surface code. X errors on qubits flip the sign of the neighboring Z's, Z's flip the sign of the neighboring X's. So then here's a question. Let's say we're just going along, because this is what's going to actually happen. We don't know where the errors are. We just get to see the minus signs. So the actual thing that we have to do is a bunch of minus signs show up in our surface code, and we have to figure out where the errors were so we can fix them. So let's say these minus signs appeared. What errors are you going to guess happened?
It would be X errors on the nearby qubit.
Which qubit?
The in between the minus, where the stabilizer Z gives minus.
So this one, so this qubit, I'll call this qubit B and this qubit A. Which qubit are you saying I should put an X error on? Okay, right, great. So there's an X error here, right? Because X errors are what flips Z stabilizers. So we put an X error there. And on the other hand here, the X stabilizers were flipped, so we know that there was a Z error there. So we likely had an X error between the Z stabilizers and a Z stabilizer between the Z error between the X stabilizers. This is fine. This is good. This is what we wanted. We're detecting errors. We're happy. Let's look at a slightly trickier case. What if we measure minus signs on these X's over here? Where should I put my errors? Where am I going to guess that my errors were? And I'll just label some qubits as A, B, C, D. Great. So this is, I'm getting 2 correct answers in the chat, but they disagree with each other. So that's interesting. Let's think about that. So the answer is there's actually two options that are both equally likely. So one of the options, which was said in the chat, I'm going to call E1, and it just, you know, the error chain kind of looks like that. That's one option. The other option, I'm going to call E2, and the error chain looks like that. And we don't know which one of these happened. We literally have no idea. They're both equally likely. Like they both involve two Z errors happening. And like, we really can't tell the difference because we only see the ends of this error chain. There are also very unlikely errors that could have happened. Like it could have been like a Z there, 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 and a Z there. And then we get an error chain like that. But that's unlikely. We're not gonna guess that that happened. We're just going to guess that, you know, one of these two errors happened. And the question is, does it matter which one of these we chose? Because if every time two errors happen, we guess the wrong two errors and we just screw up our code, then we're in trouble. This is not a good code. That won't protect us against large errors. So the question is, does it matter which one we pick? And the thing to realize is that E1 times E2 is the stabilizer SK. Right? It's the stabilizer ZZZZ, which means that E1 is just E2 times SK. So what does this tell us are the effects of E1 and E2 when we act on a state? Well, that means that E1 acting on our state is the same as E2 times SK acting on our state, because these are two equal operators. But remember, SK is a stabilizer of our state. So SK acting on our state doesn't do anything. What that tells us is that E1 acting on our state and E2 acting on our state are actually the same thing. So if we guessed that E1 happened, or if we guessed that E2 happened, we're not wrong, because both of them do the exact same thing. And if we try correct one of them, but the other one happened, well, we still get a correct answer. And so this is like one of the things about the surface code that the more you think about it, the more you realize how clever and beautiful it is, because it's really hard to actually figure out what errors happened in the surface code. Usually, when you see a bunch of error-like locations, when you see a bunch of minus signs, there are many things that could have caused that error. And the key thing to realize about the surface code, and the more you think about it, is that most of the things that could cause this error actually don't, like most of them have the same effect on your state. It doesn't matter which one you think it is. In fact, even this long, stupid chain that I wrote down, if you think about it long enough, you'll realize this long, stupid chain has the same effect as either one of these short chains on our state. So we could have even guessed this long, stupid chain and we would have been okay. We can guess pretty badly and be okay. And this is why the surface code is so powerful. So if it doesn't matter which one of these chains we pick, and we're still going to protect our information, the question is, what could damage our information? And up here, I have some reminders, and we're really only concerned about these two reminders. So assume we start in a state psi where every stabilizer is 1. What errors could cause our logical qubit to be damaged? So here's another exercise. So let's say we measure these two minus signs. Then somebody tell me what errors we probably had. And I'll label some qubits again, A, B, C, and D.
Z error on B and C.
Yeah, so B and C, that's one possibility. Can anyone see the other possibility?
Z on A and D?
Exactly. Okay. So there's two possibilities. There's a Z on B and C, or a Z on A and D. And both of these result in the minus signs that we've seen. One, we just see the ends of that error chain and the ends of that error chain. And in the other, we see the ends of this error chain, depending on how we look at it. So there's two possibilities. And this is going to be like hard to show satisfyingly over Zoom. But if you think about this long enough and just try out different things, you can see for yourself that there is no stabilizer, so that E1 equals E2 times some stabilizers, maybe multiple stabilizers even. This is never true for any stabilizers. It's not true that these two things are related by a stabilizer. And so the one time where we screw up is if we have this string that could either attach us to the edges, so either our error string goes off the edges, or it goes through our stabilizer. And that's the way that we mess up. These two errors are not equivalent, and they will screw up our code because they aren't related by a stabilizer. And let me just note that there's a similar thing that happens for X errors, where let me just draw on here. If we had a minus sign here and a minus sign here, we could have had an X and an X there, or we could have had an X there. We can't tell the difference. And again, this string that reaches from the top to the bottom of our code is going to actually change what our state is. And so it's actually going to cause the qubit to be damaged. So it only took 2 errors to damage this qubit, because it took 2 Z errors to put us in a state where we couldn't tell what the correct way to correct our code was. So let me just ask this question. No, so Shivanshu, the point is that E1 is not equal to E2. E1 and E2 give us the same minus signs, but they're not related to each other. So let me think about how I want to say this. Let's go back to the repetition code. So the repetition code has clear screen, sorry. Okay, so the repetition code has 3 qubits, and the stabilizers are Z1, Z2, and Z2, Z3. And in the repetition code, the error X1, X2 looks the same as the error X3. And that's because X1, X2 doesn't flip this first stabilizer because it flips it twice, and it does flip the second stabilizer. And similarly, X3 flips the second stabilizer, but it doesn't flip the first stabilizer. So these look the same. However, they aren't the same error. So if we started in the state 0, 0, 0, let's say that was the state we were trying to store. This is one of the states we can store using the repetition code, because we can store any state that looks like alpha 0, 0 plus beta 1, 1, 1 in the repetition code. So let's say we were trying to store the state 0, 0, 0. If it got an X1, X2 error, that would map it to the state 1, 1, 0. And if it got an X3 error, that would map it to the state 0, 0, 1. And the key thing to realize is, let's say we're in this situation over here. So there was an x1, x2 error. But we thought there was an x3 error. So we think there's an x3 error, even though we weren't right. Then what are we going to do? We're going to try and correct the x3 error by acting with x3 again, because x3 flips us back if we thought there was an x3 error, right? If we were down here, the correct thing to do would be to put an x3 on there and then get back to our correct state. So if we think we're down here, but we're not, we'd do an x3 and we'd go to the state 1, 1, 1. And so what we see is that x1, x2, and x3, it's important to know which one we're in. If we think we're in x3 when we happen to have x1, x2 occur, then when we correct it, we'll have changed our state entirely instead of done the correct thing and sent us back to the correct state. So there are two errors that occur here. We think one error occurred, but it was actually the other error. If we misidentify it, something really bad happens. And just because these two errors look the same to our stabilizers doesn't mean they're doing the same thing under the hood. And so similarly, E1 and E2, they both look the same to our stabilizers, but if we think E1 happened when E2 actually happened, then we'll end up changing our state. I'm glossing over some details here because, interest of time, but this is what happens. Okay, so somebody asked a question in the chat. It seems like the string of errors that go across is the problem. So why don't you just use the toric code? Well, it turns out on the toric code, we have some donut. And then it turns out that, okay, so we've kind of joined this edge and this edge to make a donut. But it turns out that a string of errors that goes around the donut, like that, is just as bad. It also destroys our state. So either we go from the edge to the edge in the surface code, or if we wrap the edge, it's just going around the donut, and that's also bad. Both things are bad. So there's no advantage in that sense from the toric code versus the surface code. But there's a disadvantage, which is that you have to somehow put it on the surface of a donut, which is hard. Okay, so it only took 2 errors to damage this qubit. It only took 2 errors to make us confused as to whether we were going off the edge of our surface code or whether we were going through the middle of our surface code. So what should we do to make the surface code better? What should we do to make it more resilient to errors? If you just look at this picture. Anyone can answer with any thoughts. How will we make it harder to confuse between joining to the edges or joining through the middle? Okay, here. I'll just show you. So the point is the surface code, you can make it arbitrarily large. So here, previously, we had this small patch of surface code. And so the probability of connecting these 2 errors through the code was the same as connecting these 2 errors to the edges. But if we move the edges further away, it's clearly true that if we get these 2 errors, we shouldn't try and connect this error all the way to the edge over here and connect this error all the way to the edge over there. That's wrong. We just connect them through the middle. And then it's not ambiguous anymore which error string we should pick. This is a bit of a sketchy statement, like, are you sure it's better to make it bigger? Because when you make it bigger, you also increase the number of like places there could be errors. But you can actually prove with like a lot more work that just making it bigger and bigger and bigger does make it better and better and better, as long as the error rate isn't too high. So the essential point of the surface code is we have been studying a very small patch of surface code that can correct, you know, 1 or 2 errors, depending on where they occur. But the reason the surface code is much better than Shore's code is that for the surface code, if you're getting too many errors still, if you're still not satisfied with how well the error correction is going, you just add rows and columns. And as you make the surface code larger and larger, you decrease the likelihood that one of these errors that joins the boundaries occurs. Okay, there's a chat. Is this approach feasible in terms of resources required for computation? Definitely not right now. Definitely not right now. You can, I mean, there are like ways to optimize this, but I think you should, one nice thing about the surface code is that the error rate decreases exponentially every time you add a row and a column. So this is feasible in a scaling sense. It's very, very good in a scaling sense. Like you can, like basically every time you add a row or a column, you should expect the error rate to halve or something. So you can get really good error rates. And if your error rates are still bad, you only increase the size of your computer a little bit, and then they're really good. That said, you can do some resource estimations, and resource-wise, it's estimated that if you're using the surface code, you should expect to need between like 10 million and 100 million qubits to do anything interesting with the surface code. That doesn't mean that a single patch of surface code has like 10 million qubits in it. That means that if you want to do a computation that involves hundreds of logical qubits, hundreds of error-corrected qubits, you're going to need millions of qubits to build all of the little patches of surface code you'll need to store all of the quantum states you need to store. And yes, there is a great reference for this that I will put up on the next slide. So I want to leave you with kind of a final thought. This is once you look at this huge patch of surface code, and this is the best possible thing we have for correcting errors right now. This is what everybody thinks is going to be the first error correcting code as of right now. There's maybe room for improvement, but this is a fun interaction that I saw in a presentation a few weeks ago. It was a presentation by this guy, Steve Lamia, who works at Amazon Research. And he had this line where he said, you should think of a quantum computer as a device that does error correction 90% of the time and just occasionally applies a gate, which is not exactly the way you think of a quantum computer when you're like building things in Qiskit, because Qiskit, you just apply gates everywhere. But actually error correction is going to make up the majority of a duty cycle of a quantum computer. Most of the time it's applying error correction. And so he said a quantum computer is a device that does error correction 90% of the time and occasionally applies a gate. To which Steve Gervin, who's a professor here at Yale, replied, I think you meant maybe 99%, because it's really, really hard to do error correction, and you're going to devote a lot of resources to it in any computation. It's kind of the main thing a quantum computer will do. And so I think I've given you some of the tools to start exploring and understanding it, and I think it's a very exciting area because, again, it's most of what your quantum computer is going to do. So in summary, what did we talk about today? We started kind of fiddling around with the stabilizers of the surface code. And we figured out how these stabilizers allow us to detect X and Z errors. And we saw how we can make it better and better by making it larger and larger, which is something that you can't really do with source code. And so I haven't addressed a lot of things about the surface code. I've glossed over many, many things. There's many, many pieces that you need to like put together to actually make the surface code work. And these pieces weren't all realized at the same time. They were realized in successive papers. And it's kind of miraculous because it's not obvious to me that just because the error correction works, that everything else works. So we haven't addressed how do you put qubits into your surface code and how do you read them out? How do I like measure a qubit in the Z basis or something if it's encoded in the surface code? I also haven't told you how do you perform gates on qubits that are encoded in a surface code. Let's say you have a qubit that's in a piece of surface code. How do you do a Hadamard gate to it? How do you do an S gate to it? How do you apply an X operator to it? These are all good questions that I haven't addressed. How do you actually measure these stabilizers? I've just been saying measure the ZZZZ operator. That's not just like a thing that Qiskit naturally has. That's not a thing that any quantum computer naturally has. But there are ways to carefully measure the ZZZZ operator without individually measuring the qubits in the Z basis, because you're not allowed to individually measure these qubits in the Z basis. That'll collapse your state. You have to measure just ZZZZ. And if you're very worried and very like rigorous here, you would worry that if you're measuring the stabilizers, what happens if sometimes you measure the stabilizer incorrectly? Like you think it's a 1, but it was actually a -1. Does this code still work if you sometimes measure stabilizers incorrectly? The answer is yes, but you have to work a lot harder. And then finally, you could ask this question like, how much noise can you handle before the code stops working? And this is called the threshold error rate, where after a certain point, if there's too much noise, making the code bigger and bigger just adds more noise faster than you can correct it. So you don't want to make the code bigger anymore. But below the threshold error rate, every time you make the surface code bigger, you win. And the best reference in the world for the surface code is this archive paper over here. It's archive 1208.0928. If you just Google that, it's a paper from 2012. So parts of it are a little out of date, but the pictures are very nice. It's very, very step-by-step and friendly in how it's explaining all of these questions. The only thing to warn you about it is that when they talk about how do you perform gates on qubits, they're using an outdated method to perform the gates. So when they talk about braiding, you can and should try and understand braiding. It's really beautiful and interesting, but you should also in the back of your mind know that this is not the state-of-the-art way to apply gates to the surface code. And there's other stuff out there, but this is still a wonderful paper that is kind of the standard reference that everybody recommends. I posted this in the Discord as well, so you can check it out there, or you can write down the archive number now. Yeah, and okay, so let's answer some final questions in the chat. So are there any other promising error correction codes other than the surface code? So the surface code is the winner in terms of threshold error rate. What do I mean by that? I mean that it's so if you have qubits that are too noisy, none of these no code works. If the qubits are too noisy, then just trying to use this code introduces more noise than it corrects. And so you're wasting your time. The surface code, as you make your qubits better and better and better and better and better, the surface code is the first code that starts working. So there are some codes that require your qubits to be better than the surface code. So like your qubits have this much noise, nothing works. Your qubits have this much noise, the surface code works. Your qubits have this much noise, other codes work as well. So people seem to think that the surface code is going to be the first code that works. But that doesn't mean it's necessarily the best code if we get our error rates down all the way down here. There's another popular code that's called the color code. And it's also a stabilizer code. So you can also understand it using everything that we've developed today. And it requires better qubits. But if your qubits are good enough, it requires fewer qubits than the surface code. So there's some crossover where like the surface code wins if your error rate is here, the surface code wins if your error rate is here. The surface code wins still if your error rate is just below the threshold. But then if it's far enough below, the color code wins. So that's another option. And those are kind of the two main two main error correcting codes that run around out there. So then, won't it adding more qubits for error correction increase the computational complexity of the algorithm we want to apply? And this may not lead to an advantage over classical computation. Yeah, so absolutely. So the thing about the overheads of error correction is that error correction is exponentially good at correcting errors, which means that if your quantum computer is doing something exponentially better than a classical computer, even after you do error correction, it's still going to be doing something exponentially better than a classical computer could. And the thing to realize is that, like, if you want to do error correction for some computation, you might need surface code patches that are like 10 by 10. And if you want to like double the length of that computation, in order to correct errors for that, you might need surface code patches that are like 11 by 11. And to double that computation, you might need surface code patches that are 12 by 12 or something. But the point is that increasing the length of the computation doesn't actually increase how much surface code patch you need very much, because just making the surface code a little bit bigger drastically improves it. That said, the overheads are really intimidating. And so I think the official position at Google right now is that any quantum algorithm that promises a polynomial speedup, so this is, for example, Grover's algorithm, any quantum algorithm that doesn't prove an exponential speedup, I mean, you still can get quantum advantage, but the base rates, the overhead, the number of qubits that you need to just get started doing error correction is going to be so huge that it's almost certainly not worth it, at least unless we get very, very, very good at building qubits in a way that we are not right now. Okay, has the surface code completely replaced the short code in all applications? Yes, absolutely. I don't think anyone is trying to build the short code. Short code might be fun in like some sort of like basic experiment, like if somebody's trying to be like, oh, I think my qubits are getting pretty good, I'm gonna just, but I don't have very many of them, I only have 9 of them, I'm gonna just try building the short code and seeing if it reduces the error rate at all. That's a fun little experiment that I'm sure people are working on. But for any practical large-scale quantum computing, we're aiming for the surface code, not for source code. And I should say that, like, as far as replace the short codes in all application goes, nobody's actually realized the surface code. Nobody's managed to build qubits that are both high quality enough and there are enough of them. Like, you need both high quality qubits and you need many of them to realize the surface code. And nobody's got that combination down yet. People have like small systems of like 2 or 4 qubits that they claim have good enough error rates that they might be able to build the surface code, but then scaling up the production has been challenging. So all the pieces aren't there yet. And then, yeah, too noisy, what does that mean? Does it mean higher frequency of error than the possible frequency of correction? That's essentially right. Yeah, it means that each time you do a measurement of these stabilizers, too many errors have crept in for you to be able to reliably correct them. So you need your qubits to be good enough, or your measurement of the stabilizers to be fast enough, you know, some combination of those things, so that every time you measure the stabilizers, there haven't been too many errors introduced for you to reliably figure out where they were. Okay, any other questions? I think braiding in topological quantum computers should be errorless. Why isn't this type of computer more popular? It's not quite errorless. It depends on the type of quantum. It depends on the type of topological quantum computer you have. But I think most topological quantum computers will still probably need another type of error correction on top of them, unfortunately. This is still an open research question, but nobody's managed to even observe a single anion to braid it yet. People think they have seen these things, but it's like very controversial. and nobody's actually proven that they have an anion that they can break. I mean, Microsoft is working very, very heavily in this area, but they have essentially zero results yet. That doesn't mean that they won't one day, and they might leapfrog like Google and IBM and others, and I think that's their hope. But braiding in topological quantum computers is still like, it's not clear that it will ever work. And another thing to say is that the surface code is us kind of trying to mimic a topological quantum computer just using normal qubits. And when we do braiding in the surface code, we're trying to kind of mimic braiding using topological qubits, but we're doing it in kind of a more controlled way where we can actually prove that we have good error correction. Okay, so then somebody said, what's the deal with bosonic codes? Bosonic codes are an entirely different thing. How do I want to say this? So the idea with bosonic codes is you're just trying to make a qubit. The only goal with bosonic codes is this is like a way to make one of these qubits very, very good. So the bosonic codes are something to do to make one qubit not have too many errors in it. Then you would still need to take those bosonic qubits and stick them into another higher level code like the surface code to correct all of the remaining errors. But the idea behind bosonic codes is that a qubit is something with like two quantum states that we call 0 and 1. A bosonic code it's usually thought of as like a simple harmonic oscillator, if some of you have taken physics, and it has energy levels. And the point is just that it has lots of states. In fact, has an infinite number of states. So it has a state 0, it has a state 1, it has a state all the way up. And so the question is, can you use a bosonic system that has all of these states to encode a qubit? And one easy way to do it would be to say that, okay, this is the qubit 0 state, this is the qubit 1 state, and all of the other states are garbage, never go there. But that turns out to not be the best thing to do. It turns out that the best thing to do is some version of store 0 as a superposition of this state, that state, all the way up, and store 1 as a superposition of this state, dot, 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 all the way up. And you can do some manipulations to make these error rates, if you store the qubits like this, very, very low. And those manipulations go by the name like bosonic codes. This way of deciding that this superposition is 0 and this superposition is 1 is called an encoding of the qubit into the bosonic modes. This is a bosonic code for a qubit. And then you just try and reduce the error rates by choosing the best code here. But this is an entirely different thing than the surface code or any other quantum error correcting code. It's just saying that I have some little piece of hardware, I want to store a qubit inside it. What's the way to do that that reduces the error rate the most? And this is something that was essentially invented at Yale and continues to be developed here, just as a plug for my current institution. Yeah. Okay. Any final questions?
If there are no more questions, we can wrap it up, but make sure you join our talk next week. I will put the information in the chat if you give me 1 second. But thank you to all of those who attended our 3-week session, and we hope to see you in Discord community for more events like this.
Yeah, thanks everyone. And if you're trying to work through this reference or anything else, trying to understand error correction better, This reference is really self-contained, so I think you can just like pick it up and read it. But yeah, message me on the Discord and I'm happy to help. Okay, have a good day, everyone.